everyone. I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. So in my previous videos, in my last video, we have discussed about the phenomena of diffraction in detail based on Huygens wave theory of light, where we talk about the diffraction phenomena is because of spreading of secondary waves, and these secondary waves, they are originating from different points of primary wavefront. And also we have discussed about different types of diffraction. So in that we have discussed about Fresnel diffraction as well as Fraunhofer diffraction. And these two types of diffraction, they are based on what type of wavefront we are using in order to produce diffraction. So here also we have discussed about three different types of wavefront: spherical, cylindrical and plane wavefront. And if you are making a source, or if you are keeping your source at finite distance from the obstacle, then we'll be making use of spherical or cylindrical wavefront. Then that case is applicable in case of Fresnel diffraction. Whereas in Fraunhofer diffraction, we'll keep our source and screen at infinite distance. So what type of wavefront we'll be making use of? The plane wavefront. And also in our previous video, we have discussed about Fraunhofer diffraction at a single slit. So if we take a single slit, and if we make our plane wavefront, because we are talking about Fraunhofer diffraction, so what type of wavefront will be considering? Will be considering plane wavefront. And how we'll get plane wavefront? For that, we have to keep our source at infinite distance. So if we keep either a point source or extended source at infinite distance, then whatever spherical or cylindrical wavefront coming from that source, it will be limited in a small region. And that limitation of spherical or cylindrical wavefront in small region will give rise to plane wavefront. And what is the direction of propagation of light in case of plane wavefront? It will be perpendicular to the plane wavefront. So here, there we have taken plane wavefront and we made it fall on a single slit, and the width of the slit is very, very small. So slit width is very, very small. And what happens once the plane wavefront falls on that slit? After the slit, so we have spreading of secondary waves. And what we have done, those secondary waves, using convex lens, we have focused them on different points on the screen. And then what we have observed here is, on the screen, what type of pattern is recorded because of single slit. There we have seen that pattern recorded on the screen. We have maximum intensity. We have seen that maximum intensity is at the center. So we have maximum intensity at the center, and it is called as principal maxima. And then we have minimas on either side of principal maxima, and between the two minimas I have secondary maximas. So here all bright fringes, they are not of same intensity. Maximum intensity is at the center, and when we go for other bright intensity, their intensity keeps on decreasing as order increases. This is the pattern we recorded in case of the single slit. Now today we are going to discuss what type of pattern will be recorded on the screen because of Fraunhofer diffraction from large number of slits. So what happens if I keep many number of slits in front of plane wavefront? So that we are going to discuss now. But before that, we should get familiar with one important term. And what is the term called as diffraction grating? Okay, so this is also called as actually plane transmission grating. But first we'll see what is diffraction grating. So here, grating is nothing but an arrangement which consists of large number of parallel slits, and these slits are separated by equal opaque spaces. So what is our grating? Suppose I have taken a large number of slits. It consists of large number of openings, and all these slits, they are of same width and they are separated by same width of opaque spaces. Now how to get such arrangement? So for that, what we are doing here is generally how to construct a grating. For that, I'll take transparent material And this transparent material, it is nothing but our glass. I have taken a glass material, which is a transparent material. Now using fine diamond point. So using fine diamond point, I am going to draw rulings on this glass plate. So what do you mean by rulings? This is just like scribbing. So I'm drawing fine lines, and these are vertical lines. And when you're drawing these lines should be parallel and they should be equidistant from each other. They should be equidistant from each other. So I'm going to draw rulings, and these rulings, they should be equidistant parallel lines. Okay. And what is the use of drawing such rulings? See, suppose if we have scratch on our glass, then at that part we will not be able to see clearly. It means that it won't be transparent to light, it will be opaque to light. So wherever we have such rulings, if you see this particular figure, in this figure also what I have done, I have taken transparent material, usually glass, on that using fine diamond point, I have drawn these lines. And these lines, I'm saying they are opaque to light. They won't allow light to pass through them. Whereas if you take space between two adjacent lines, it will act as slit, and this slit, it will allow light to pass through it. So because of this arrangement, I am going to get large number of slits. And what is the width of slit? The width of the slit is E. And what is D? D is width of each opaque part. So here D is width of each opaque part and E is the width of each slit, and E plus D, it is known as the grating element. And such constructed grating, it is called as plane transmission grating. So it is called as plane transmission grating. So which is constructed by taking a transparent material such as plain glass and using fine diamond point, drawing vertical lines. And what we have to see here is all these lines, they should be equidistant from each other, and this space between two adjacent lines, it will act as a slit. Such arrangement having large number of slits is nothing but grating. Now next we'll see what happens when we make our wavefront, plain wavefront falls on that grating. So what type of diffraction pattern will be recorded on the screen because of such grating, diffraction from grating. So next we are going to discuss, and before that we should get familiar with certain terms. As I told you, what is E? E is the width of, so here we can take vice versa also. E we can take width of the slit, or E also we can take width of the opaque space, and D as the width of the slit. It's up to us. So E plus D, it is called as grating element, and N is number of lines per inch. See here, usually you may wonder how many lines we can draw on this particular transparent material. So we can draw around even 30,000 lines per inch. So LPI means lines per inch. So within this inch, we are going to draw how many lines? 30,000 lines. So just imagine how closely spaced these lines are. Okay. So this number of lines per inch, it is denoted by capital N. Into E plus D is our grating element. Where one is width of the slit, other one is width of the line or that ruling. So here within that inch, 1 inch, and we know that 1 inch is 2.54 centimeter. So this E plus T, we can write it as 2.54 by N centimeter. Okay, so we can have around 30,000 lines per inch of a grating. So you'll observe that width of the slit will be very, very narrow, and they will be comparable with wavelength of light. And why they have to be comparable with wavelength of light? Then only our diffraction will take place. So what is the important condition for diffraction to take place? Wavelength of light should be comparable with the size of the slit. So now once that wavefront falls on such particular grating, you'll observe that there will be formation of the spectrum, and that spectrum, it is called as diffraction spectrum. And when you are taking such n number of slits, and when you are considering diffraction, there is not only diffraction but interference is also involved. This is very important point. When you take single slit, completely we'll be talking about diffraction. But when we take n number of slits along with diffraction, there will be also interference of diffracted light. And because of both diffraction and interference of diffracted light, we'll get spectrum. And that spectrum, it is called as diffraction spectrum. So next we are going to see how we are going to get that spectrum. So now I'm going to discuss about Fraunhofer diffraction due to N slits. That is nothing but grating. So here, as you can see, this is our plane transmission grating. So this is our plane transmission grating. What is plane transmission grating? Where we have taken a plane mirror, and on the plane mirror we have drawn rulings so that we can get slits. Okay, and here, as I told you, vice versa. So what is E? E is width of each slit and D is width of each opaque part. So and E plus D is our grating element. Okay, and because we are considering Fraunhofer diffraction, so what type of wavefront we'll be using? We'll be using plane wavefront of monochromatic light. And what is the wavelength of that plane wavefront? It is given by lambda. And what is our obstacle or slit? It is nothing but a grating which has got how many number of slits? It has got n number of slits. Okay, once your wavefront falls on such grating, then what will happen? Diffraction takes place. What is diffraction? Diffraction is nothing but spreading of secondary waves. And from where we'll get these secondary waves? These secondary waves are coming from each and every point of primary wavefront. So out of this grating also you will have secondary waves spreading out in all possible directions. So just like we have done in single slit, here also what we'll do, whatever secondary waves are spreading out of the grating, we'll try to focus it on the screen. For that we'll make use of lens. So this is our lens. So now this lens we have to use because our screen it is kept at infinite distance. Okay, now here also I'm taking two sets of secondary waves. So first set of secondary waves which are shown by dotted line. If you see these dotted lines, these are the secondary waves which are traveling exactly normal to the grating. So they are traveling exactly normal to the grating, or where we can say that theta is equal to 0. All those secondary waves, so which are shown by these dotted lines, what I am doing using this converging or convex lens, I am making them focus at one particular point. And what is that point? Point P0, which is center of the screen. And we know that path difference between these secondary waves which are traveling exactly normal to the slit, their path difference is 0. And path difference is 0 being it is a condition for bright fringe. That's why our point P0 will be bright. So here you will have central bright image. At the center you will have central bright image. And how this point P0 is formed? It is because of all those secondary waves which are traveling exactly normal to the slit. Now what is my next step? Next step is now considering all the secondary waves which are making angle theta with the normal direction, which are shown by the solid lines. So I'm considering all the secondary waves which are making angle theta with the normal direction, and using this lens I'm focusing them at point P1. Again the same thing, I should try to get condition when this point P1 will be bright and when this point P1 will be dark. As we have done in case of single slit, in order to get conditions for bright and dark, what we have to do first, we have to find path difference. So now if I take these two waves, so here I am taking the two waves coming from, so actually what you will observe here is there are many slits, and from each slit, if I take each slit, from each slit I'll get one diffracted wave, and the diffracted wave from two adjacent slits. What is their path difference? In order to find path difference, I have to draw one normal. So this is the normal drawn. Okay, suppose this I'm calling it as, this is P and this is drawn one normal like this. So if this is Q and if this is R, okay, then this angle will also be theta. And if I take this triangle, then what you will observe here is sine theta is equal to opposite side, that is nothing but our path difference, by PQ. What is PQ? PQ is distance. See here. So this is my slit and this is also my slit. I have one wave going in the direction theta. This is all another wave which is going in this direction theta with respect to normal. So these are the, so if I consider normal direction like this shown by dotted line, this is also normal direction shown by dotted line. So I have two waves. So this angle is theta. Okay. Now, in order to find path difference between these two waves, I have drawn one normal like this. This is our normal. So this point is P, this point is Q, and this point is R. Okay. Now QR is nothing but a path difference, QR. So it is given as PQ sine theta. But what is PQ? So as you have seen that this total width is E and this width is D. So this width, it comes out to be E by 2. And this width also, it comes out to be E by 2. So this PQ, I can write it as E by 2 plus D plus E by 2 sine theta. Okay. So your path difference, it comes out to be E plus D sine theta. This is the path difference between the two successive secondary waves which are making angle theta with the normal direction. So here we have seen that. So that path difference, it comes out to be E plus D sine theta. And apart from this, what we have to understand here is one very important point here is, as I told you, we have many number of slits. So in this case, we have many number of slits. Now from each slit, we'll get one diffracted wave. This is our diffracted wave. We'll get one diffracted wave. And we have seen that in case of single slit, this diffracted wave amplitude, it is given as A sine alpha by alpha. And what is alpha here? Where alpha, it is given as pi by lambda sine theta. So alpha, it is given as pi by lambda sine theta. So like this, how many number of diffracted waves I'll get? Total, I'll get n number of diffracted waves. So we'll get total n number of diffracted waves, and each wave amplitude is A sine alpha by alpha. Now how to find phase difference between two adjacent waves? Further, we know the path difference. So here, if you consider here, now what is our point P1? This is because of secondary waves which are traveling in direction theta with the normal direction. Now, in order to find intensity at point P1, what we have to do? We have to apply the theory of Fraunhofer diffraction at single slit. And we know that from each slit, I'll get one diffracted wave whose amplitude is A sine alpha by alpha, which is starting from the middle point of this slit, and we know alpha is given by pi by lambda E sine theta. And what is the path difference between two consecutive slits? E plus D sine theta. I think in the last case we have seen, so that the path difference, it has come to be E plus D sine theta. So if we know path difference, how we can find phase difference? What is the relation between phase difference and path difference? Phase difference is 2 pi by lambda times the path difference. And suppose this 2 pi by lambda times E plus D sine theta, it is nothing but 2 beta. Okay. So now next, what you will observe here is, because we have n number of slits, I'll have n number of waves. Okay. What is the amplitude of each wave? Amplitude of each wave is given by A sine alpha by alpha. And what is the phase difference between two adjacent diffracted waves, which is given as 2 beta? Then we have again method of vector addition of amplitudes. So if you consider method of vector addition of amplitudes, according to this method of vector addition of amplitudes, if you have n number of waves, okay, and amplitude of each wave is small a, and if phase difference between two consecutive waves from these parts is d, if this is the phase difference, then from the method of vector addition of amplitudes, resultant amplitude, it is given by A sine nd by 2 by sine d by 2. So sine nd by 2 by sine d by 2. So, but in our case, what is our amplitude? Amplitude of each diffracted wave, it is given by A sine alpha by alpha. And how many number of waves? Instead of small n, I have capital N. And what is my phase? Phase is 2 beta. Okay. So now, if I make these substitutions, R is equal to, in place of A, I am going to substitute A sine alpha by alpha. Okay. Sine. And here, in place of small n, I'll have capital N into 2 beta by 2. Then in the denominator sign, what is d? D is 2 beta by 2. Okay. So this 2 will get cancelled. So you end up having resultant amplitude as A sin alpha by alpha into sin n beta by sin beta. And of course, once we know amplitude, how we can get intensity? Intensity is square of it. So A sin alpha by alpha whole square into sin n beta by sin beta whole square. So what you'll observe here is, in this case, this A sin alpha by alpha. So A square, I'm taking it as I naught. So this factor, as we know that it is because of intensity distribution from a single slit, from each slit, whatever intensity we are getting, it is given by A sin alpha by alpha square. And in addition to that, in case of grating, in case of n slits, we are getting one more term, which is sin n beta by sin beta whole square. And we'll observe that this particular term, it is because of intensity distribution as combined effect of all the slits. So two terms, one is because of diffraction from single slit, another term because of combined effect of all slits. Now next, once we get intensity, we'll try to see the point P1 on the screen, which is because of secondary waves making angle theta with the normal direction. So what are the conditions to be bright and what are the conditions to be dark? So in order to consider those conditions, so first I'll talk about principal maximas. So first I'll talk about principal maximas. So if I take this principal maximas, now intensity, now what is the expression for intensity I got? I is equal to A sin alpha by alpha whole square into sin n beta by sin beta whole square. Okay, I'll not consider this condition because this condition we have used in order to find intensity distribution from single slit. Now I should try to get conditions in terms of beta if I have to get the combined effect of all slits. Now when this value will be maximum? I'm saying that this value, it will be maximum if sin, I'll get maximum intensity. When I'll get maximum intensity, for that I have to take sin beta is equal to 0. But at the same time, sin n beta should not be equal to 0. Okay. And if I take this condition, I end up having beta is equal to plus or minus n pi. So I'll have beta is equal to plus or minus n pi, where n is equal to 0, 1, 2, 3. And how I got this? Okay. For that, I'm making use of Hospital's rule. So if I make use of Hospital's rule, if I consider my beta value to be plus or minus n pi, then this particular ratio sin n beta by sin beta, so this I can write it as, so using Hospital's rule. So here this will be equal to, when I have to differentiate beta both numerator and denominator. And if I differentiate sin n beta, I end up having n cos n beta, and sin beta will become cos beta. And if I substitute beta is equal to plus or minus n pi here, so this will give rise to 1. Even cos beta will also give rise to 1. So here, because cos 0 is 1, so you end up having maximum value n. And square of intensity will be n square. So intensity will be maximum if I take sin beta to be 0, but at the same time sin n beta should not be equal to 0. So according to Hospital's rule, what is the value of maximum intensity? Maximum intensity will be n square. So this is the condition for getting principal maxima. And here plus or minus is there. So here, what is beta? So we know that 2 beta, it is defined as 2 pi by lambda into E plus D sin theta. Okay. So beta is pi by lambda, E plus D sin theta is equal to plus or minus n pi. Okay. From this is the condition for principal maximum. Very important condition. E plus D sin theta is equal to plus or minus n lambda. And plus or minus, what does it indicate? It means that you will have principal maximas of same order on either side of 0 order principal maxima. If I take n to be 0, I'll get 0 order principal maxima. And if I take n is equal to 1, then you will observe that principal or plus or minus sign shows that there are two principal maxima of same order lying on either sides of zero order maxima. See, in single slit, we got only one principal maxima with maximum intensity. But in this case, we are getting many principal maximas that too they are arranged on either side of zero order principal maxima. So that is the difference between n slits and single slit diffraction. Now we have to get the condition for minima. Now when we'll get minima, so here again we come back to our intensity expression. What is the intensity expression? A sine alpha by alpha whole square into sine n beta by sine beta whole square. We have this expression. As I told you, we are not considering this. And when intensity will become 0, here intensity will become 0 when sine n beta should be equal to 0. But at the same time, sine beta should not be equal to 0 because we got sine beta to be 0 for principal maxima. And when sine n beta will become 0 for plus or minus n pi. And here in this case, n starts from 1, 2 and so on. Now we'll see what are the permissible values of m. M may not take all values starting from 1. Okay, that will come, we'll discuss later. But this is the condition we got for minima. We know what is beta. Beta is pi by lambda e plus d sine theta. Now I am getting this condition for minima. Now, what are the values taken by m? You will observe that m, okay, it will start from 1, 2, 3, so on. It can take values till n minus 1. And m, it cannot take values 0, n, 2n, 3n and so on. Why these values are not permitted for m? Because if I substitute m is equal to 0, for m is equal to 0, I'll have e plus d sine theta is equal to 0. This is the condition for principal maxima. And if I take m to be n, if I substitute m is equal to n here, so n into e plus d sine theta is equal to plus or minus n lambda. This will get cancelled. And this condition again it is for principal maxima. So if you substitute all these values in this condition, you will get condition for principal maxima. So that's why I have to limit my m values to 1, 2, 3 and so on to n minus 1. It means that how many minimas are possible? Only n minus 1 minimas are present, and that too they are present between two adjacent principal maximas. Okay, now coming to secondary maxima, just like we have done in single slit. So for any function to be maxima, its first derivative should be equal to 0. So this has to be equal to 0 with respect to beta. I have to differentiate with respect to beta. And if I differentiate, so I'm considering only this term. And if I simplify this term, so I end up having this condition. And from this condition, I will get this particular case. So we are only interested in conclusion, not in quantitative part, not in the derivation part. I have this, and what you will consider here is as n increases, intensity of secondary maxima related to principal maxima decreases and becomes negligible. So what you'll observe here is, see, in case of this n slits, we'll have principal maximas, and principal maximas, they are of different orders. And in between the principal maximas, you will have minimas. And how many minimas? N minus 1 minimas. And apart from n minus 1 minimas, from this condition, you will have how many secondary maximas? N minus 2 secondary maximas. But what you will observe here is intensity of secondary maxima will be very, very less compared to principal maximas. If you are taking n to be very large, when number of slits are very, very large, so you will not be able to see secondary maximas. So whatever visible on the screen is only principal maximas that we have to understand. So this is our intensity distribution curve. And as you can see, this is because of factor sine alpha by alpha whole square. And this is because of second factor due to combined effect of the slits. And this is our final pattern. So this is our final intensity distribution curve due to end slits. And what does it consist of? This is zero order principal maxima. So it is zero order principal maxima, right? And this is first order principal maxima and so on. And intensity of principal maxima keeps on decreasing as order increases. And maxima, principal maxima of same order, it is present on either sides of zero order principal maxima. And in between two adjacent principal maxima, I have minimas as well as secondary maximas. And how many minimas and second n minus 1 minimas and n minus 2 secondary maximas will be present. And if your n is very, very large, these secondary maximas will not be visible. Whatever pattern you are getting is only because of the principal maximas. So this is about the Fraunhofer diffraction due to end slits. Now we are going to see how grating spectrum we can get because of diffraction from n number of slits. Now suppose I have taken my grating. Suppose this is our grating which has got rulings like this. First I am making monochromatic light. So this is my monochromatic light. Suppose I have taken sodium vapor lamp. Okay. Now what you will observe here is if your n is very, very large, then your principal maximas, they'll come, they get narrowed, and these principal maximas, they will be seen as bright sharp lines. So out of your grating, you will have sharp lines coming out like this. These are the sharp, bright sharp lines, and this is the central bright line. Okay, and this is zero order principal maxima, this is first order principal maxima, and this is second order principal maxima. You are not able to see spreading of light because of secondary maximas and minimas, because if n is very, very large, secondary maxima intensity will be very, very small, and your principal maximas, they will be seen as bright sharp lines. And you will observe that as order of this principal maxima, its intensity keeps on decreasing, and maximum intensity is kept at the center, which is the zero order principal maxima. And this spectrum, it is called as line spectrum or grating spectrum. And what happens if I replace this monochromatic light? So this is our monochromatic light. What happens if I replace this monochromatic light with white light? Suppose if I take white light source. So what is the example of white light source? White light source, we have our mercury bulb. So if I take mercury bulb and if I make it fall on this grating, so what you will observe here is still at the center, you will have central bright image. So here we have central bright image. So and apart from that, in each order, suppose if I take one order, you will have splitting of colors. Okay, and innermost color will be violet color, and then outermost will be red color. So this is for first order. Similarly here also for first order. So here we have with GR. This is also first order. And similarly in second order, you will be able to see splitting like this. So here also with GR color. So here also we have splitting of colors. And here also we'll have with GR colors, and this is for second order and this is for second order. So instead of monochromatic light, if we use white light, our zero order principal maxima, still it will be white image. It will be central white image. Why? Because all the wavelengths get reinforced each other and intensity will be maximum. And when we go for other order principal maxima, in each principal maxima, you have spreading of light. Light will get diffracted and you'll be able to see different colors. And that violet color, it will be in innermost position and red color will be in outermost position. And these colors, they will become fainter as order increases, and maximum brightness it will be present at the center. And this is called as grating spectrum because of light. So here what you have seen about the grating spectrum. Now one more important point what we have to discuss here is, see what you will observe here is, if we in the lab when we perform experiment, usually if I take a grating which has got 15,000 lines per inch, Then we have observed that on the screen I am able to see maximum number 2 orders of principal maximas. So maximum I have seen 2 orders of principal maximas. Whereas if I take 2000 lines per inch grating, then I am able to see many orders of principal maximas. So why these orders are changing? So it is dependent on lines per inch, and also it is dependent on one more factor. So maximum number of orders to be seen on the screen because of a grating, it depends upon the 2 factors. What are those 2 factors? It comes from this condition for principal maxima. We have derived this condition for principal maximum. What is the condition? E plus d sine theta is equal to n lambda, and sine theta it comes out like this. And we know that 1 by E plus D is capital N number of grating lines per unit width of the grating. And we know that always sine theta it will be less than or equal to 1. So therefore this N lambda should be less than or equal to 1. So maximum number of orders possible, it is given by 1 by N into lambda. So it depends upon the 2 factors. What are those 2 factors? Number of lines on the grating as well as wavelength of light. So as you can see, if number of lines on the grating keeps on decreasing, then number of orders visible will increase. So this is very important point. So depending upon number of lines, how many slits are there on the grating, number of orders visible on the screen are going to change. So this is in detail about the grating. So I'm going to end my video here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.